MEM School of Engineering, Department of EEE, online classes, subject Digital Logic Circuits. Unit number 3, Synchronous Sequential Circuit. So last class we discussed about shift register. Now we are going to see about counters. Counters are circuit that cycle through a specified number of states. Okay, that is, it is count number of pulses. For example, in the circuit, if you on the motor for after 9 seconds means you have to create the 9 seconds clock pulses. Okay, so that will be processed. For example, if you fix the value 100, okay, that is a maximum count. It will be count for reduced with the 1 by 1, then it will come to the 0. That is a down counter. If you so for count the clock pulses, we are using the counters. There are two type of counters. One is synchronous counter, another is asynchronous counter. That is synchronous counter controlled by the common clock pulse. Asynchronous counter controlled by the previous state flip-flop outputs. So ripple counter allows some flip-flops output to be used as a source of clock pulse for other flip-flops. So same synchronous counters apply the same clock to the all the flip-flops. So asynchronous counter, the flip-flops do not change status at exactly the same time as they do not have a common clock pulse, also known as ripple counter as the input clock pulse. So ripple through the counter. So cumulative delay is a drawback. So okay, for example, if you are going to design a asynchronous counter, for example 2-bit triple binary counter. So output of one flip-flop is connected to the clock input of the next most significant flip-flops. Okay, because here we are giving the clock pulse to the first one only. First clock pulse only we are giving the first flip-flop clock pulse only we are giving the clock pulse. So remaining second clock pulse given from the previous one output. Okay, using this you can count. So first initially the timing diagram initially it will be a 00. So after execution, because here we are giving the what value, we are giving the I to the J and K. If a value of J and K 1 means it will be toggle. Okay, initially it will be a 0. Okay, then in second value will be a 1. So then we are giving to the 1. So this clock pulse will enable. Okay, then 00, 01, 10, 11 and 00 will be produced in the output. After 00 it will be again 01. There is a continuous ripple counter will use. So same as if you want to 3-bit triple binary counter means you can add extra one. That's all. So it will be work for the 000, 0100, then 010, 011, 100, 101, then 110, then triple one. So next one will be previous state 00. So next 001 like that it will be continuously moving up. So propagation delay in asynchronous circuit is a binary counter. If the accumulated delay is greater than the clock pulse, some counter states may be misrepresented. Okay, these are the propagation delay between the one clock pulse to another clock pulses. Okay, so this is the example of 4-bit triple counter that is negative edge triggered. So negative edge triggered means you have to put clock pulses as a 0. So that is we define as the bubble for the clock pulse. Then only it will be work as a negative edge trigger. States may be skipped resulting in a truncated sequence. Force counter to recycle before going to throw all of the states in the binary sequence. So given the following circuit, determine the counting sequence and in the module's number. So here they gave the diagram. You have to define the values. Okay, this is the concept. So first if you are giving 00 means what will happen. So like that you have to count. Then what is the NAND output, like that you have to follow, then you will get the answer of mod gray less than the 2 power n. Then counting the sequence of circuit in a CB order. So this is example for this. 0 0 0, next concept, next 1 0 1 0, next is the output. So now we are going to see about how to construct a asynchronous model of 5 counter, mod 7 and mod 12. Okay, all depend on the number of values. Okay, that is called decade counters. Counters with the 10 states, that is modulo 10 in the sequence. They are commonly used in the daily life. Utility meters, odometers, like that we are using the BCD counter. So design and synchronous decade counter is the example. So these are the in counting value. Then reset. Then we will get the next value. So far we are dealing with the up counters. So down counters. So for up counter we are giving the input from output next clock pulse from the this value. So we are giving last one we are putting q1 q dash value to the next one clock pulse. Now we are giving the q value to the next clock pulse. So this is the difference here. Okay. So this is the example for 3-bit up counter. This is the example for 3-bit binary down counter. Okay, these are the concept of asynchronous ripple counter. So asynchronous ripple counter are mostly on the faster than the synchronous, because synchronous circuits are connected with the common clock pulse. So every operation it is secured the common clock pulse circuit. So it will take the more time to execute, but asynchronous circuits it will less time to execute the circuit. That is the only concept we are using. But the design of asynchronous circuits will be always complex, because each state you have to refer with the previous flip flop. So you have to uh, fully controlled by the previous flip-flop. So you have to define the previous flip-flop state and which value we have given to the next one clock pulse, like that we need to define. That is the up counter and down counter. Using switches, we can define the up-down counter in the same mode. Okay, so for first one we are using up mode, second one will be down mode, like that you can use. That is a universal asynchronous ripple counter, like that we discussed. So this one synchronous counters, this will be seen in the next class. So here what is the input and output, like that we will see. So see the diagram. So this is the mod 6 counter. So only it will go up to 6. After it will be 0. Then it will recycle. After 0 0 it will be 1. Then 1 0, like that.